Today I'm going to show you what's inside of a continuously variable transmission and how it works. We're also going to take a look at why some of these Nissan CVTs fail. Now if we start by taking an overall look around this transmission, at the front here we've got a traditional torque converter just like in a regular automatic transmission. And I've got another video on how torque converters work, so make sure you check that out in the description below. Now this transmission comes out of a Nissan Murano, which means that it's actually a transaxle situated transversely for front wheel drive. Now appropriately so, we do have a transmission cooler located over here. Now the back of the top of the transmission we've got the manual valve, which is what's going to go to the gear selector on the console. There's a speed sensor over here, and then on the back half of the transmission we've got the casing where the variators sit. Now if we take a look at this diagram of this CVT, you can see that the whole system is fairly compact. Starting here at the input shaft where we've got the torque converter. Here we've got the reverse forward clutch, which is what's going to decide which direction the rest of the transmission turns in. Then we've got our primary and secondary pulleys with a belt in between, and then a counter shaft that goes directly to the differential. Now to start this assembly, I'm going to remove all these hoses and this cooler on the front half of the transmission. Snap that one off too. Okay, I'm starting to make a mess here, so just use my brother's old pants to sap up some of this mess. This is going to be a really dirty video. We'll just pop off that cooler, and there's the filter. Looks just like a regular oil filter you'd find on a car, but just like a mini version of it. I'll just pop off that electrical connector, and I'll pop off the dipstick. At least this one actually comes with a real dipstick, unlike those newer Nissans where the dipstick is sold separately. Now it's always recommended to start with the valve body at the bottom, which means that we gotta flip this over and make a huge mess. Alright, next up I'm going to remove all these 10mm bolts that hold this transmission pan on. And I'll remove that transmission pan. This is a nice thick cast aluminum pan, which I like. You can see at the bottom here we've got these two magnets. It's got a little bit of slop on it inside of here. Now at the bottom of the transmission, underneath the transmission pan, is this valve body. Now it's responsible for directing fluid flow to do different things throughout the transmission, such as adjust the gear ratios or the mode that you're in. Over here we've got the electronics portion, which is the EEPROM that's going to communicate with the transmission control module. And over here, the steel part is a transmission filter with the pickup tube. So it's actually going to pick up transmission fluid sitting in this pan here and filter it out before it circulates it throughout the transmission. And now I can remove that filter. And you can see the filter is just like a screen-like material. I'm just going to go ahead and remove all the electrical connectors over here. Now this here is the control rod that goes to the top half of the transmission that connects to your transmission shifter, and it's basically controlling this manual valve to manually select the park, reverse, neutral, or drive functions of the transmission. You can see as I move the knob from the other side here, just how that gets controlled. And I'll just remove this nut, and then remove the secondary nut. These were double nutted on. And now I'm going to remove all the 10mm bolts that I can see. Looks like we've got the sensor, because this moves back and forth according to what gear your selector is in, and it's going to send that signal out to the transmission control module. Should be able to just lift the valve body right out of the transmission casing, and we can have a closer look. Now here's a good look at the bottom of this valve body, and you can see that there's so many little holes and ports here where fluid will flow through into the transmission casing down below. And that's because this is controlling all the individual hydraulic circuits inside of the transmission to do the various things. Now you'll notice that there's also only 4 solenoids at the front here. A typical automatic transmission might have 6 or 8 solenoids, and the reason for that is because there's not that many clutches inside of this transmission. Now if we take a look at the hydraulic aspects of the control system for this CVT, you see that the transmission control module sits at the front here and takes inputs from numerous electronic components in the vehicle and turns them into hydraulic outputs. There's numerous solenoids and valves here, such as the stepper motor, which is going to ultimately adjust the valves and how big or small the pulleys are. We've got the pressure regulators here. We've also got the valves that are going to control if it's going to go forward or backward, as well as the torque converter lockup. Now if we take a look at the electrical aspects of the CVT, we've got the transmission control module, which interfaces with the other computers in the system through the CAN communication bus. It's going to take things like your accelerator position as well as your wheel speed and other aspects and compute them and turn them into electrical signals here. Now these signals can either be inputs or outputs, such as your temperature, pressure, and speed sensor, or your solenoid valves to control the fluid. Here's a look inside the transmission casing. Now there's a lot of fluid in here, so I'll just use my brother's old gym pants again to absorb some of that transmission fluid. Now very similar to an automatic transmission, at the front we've got this bell housing here that houses the torque torque converter. Inside of here is the feed for the torque converter lockup and control. And this other one here turns the oil pump inside of here, which is rotating with the speed of the engine. That way the transmission is always getting fluid flow to do its operation. Now there's a number of 14mm bolts on the inside and the outside of this bell housing here. So I'm just going to go ahead and start removing all of them. Alright, and with all the bolts free, and I'll just lift that housing off, revealing the inside of the transmission. Now taking a look at this CVT transmission, we've got the input shaft where the torque converter bolts to over here. It also spins this oil pump. Now because the torque is so high I can't spin it by hand, but if I spin this intermediate gear here, you can see that between here and here are where the variator and the belt is located for the CVT part of the transmission. Then you've got this intermediate gear over here, and then the final drive differential over here. Now I'm going to remove this intermediate gear here. You can see that this one's actually got the gears on this angle here, and that's to prevent any whining sound when the transmission is going. Now over here we've got the front differential, and that just pops right off. And I've already got a video on how differentials work, so you might want to check out the description and the link below. The only difference here to note is that this is an all-wheel drive model, which means that you're going to need an extra shaft to feed the transfer case to feed the rear wheel. For the all-wheel drive transfer case, you've got an additional set of splines in here that connects to this carrier and thus the final drive in order to send power to that transfer case to the rear wheel. Now over here on the output variator of the CVT, we've got the lock here that controls your parking pawl, which connects inside of here and it completely locks the transmission when you've got it in park. When you take it out of park, it's going to open this back up to allow it to rotate. Alright, now I'm going to remove all the 12mm bolts that hold this oil pump and its housing to the transmission. Alright, now I just got to pry this up. And then I can remove this assembly here. Now this clutch pack has a little snap ring here that I'm going to try removing. And then now I can remove this clutch pack. Now this smaller shaft on the inside here forms the input shaft to the transmission, and this other shaft on the outside here is what drives this oil pump. And you can see that input shaft here is then going to be splined directly into this clutch over here, so this clutch is going to move as part of the input of the transmission. Now the oil pump is located inside of this housing. Now I'm going to remove these 6mm hex bolts so we can have a closer look. And with all those bolts free, I'm going to split this oil pump. And inside this oil pump, you'll notice that there's a lot of other fluid passages for fluid to come in and route its way around and also provide pressure to other things in the transmission. Over here, we've got the heart of the fuel pump here. It basically rotates around this shaft, which is offset from the housing, and as it rotates that way, you can see that the fluid is going to travel in between here and kind of get forced in between these teeth as it rotates around, and that's what provides that fluid flow. Now at the top here we have these two hex bolts, have a spring on the inside here, and that's for pressure regulation. Now if we take a look, we've got a planetary gear set in a CVT transmission, just like in an automatic transmission. Now the real reason why this is here is to provide you a reverse direction so you can actually back up your car, as opposed to just change the gear ratios the way an automatic transmission would. Now the first part of that planetary gear set is comprised of this clutch pack. Now it's powered off of the oil pump. It's got these holes in here that are going to press up against this piston here to tighten up this clutch inside of here. Now this set here houses the ring gear for the first part of the planetary gear set, and it's got these teeth inside of here that are teethed to this gear over inside of here. So essentially when this clutch locks up, it's going to lock the ring gear to these teeth inside of here, and that's going to lock it to this piece over here. Now this piece here is the sun gear of the planetary gear set. And then inside of here, you have the planet carrier. And you can see the little planets inside of here. Now this planet carrier is splined over here to this clutch sitting on the inside of the casing here. So it's actually going to lock the casing to this planet carrier when it's engaged. There's just a little snap ring here that I'm going to remove. And then I can remove this set of clutches. Next we've got another clip here that I'm going to remove. And then I can remove this return spring over here, and this just helps to return the clutch pack to its proper position once the fluid pressure is released. And then next I'll just remove this piece over here. Got a bit of fluid on it. Alright, now we're going to flip the transmission over and make some mess. And I'll just come with my brother's old underwear to sap that up, because I don't want to mess up my cardboard studio. This is going to be one really dirty video. I'm going to use a pry bar. Holy crap, that's heavy. Oh, whoa. So here we have the heart of the continuously variable transmission. This here is your input pulley, and this one is the output pulley. It's got this gear on it that's going to interface with the intermediate gear and then the differential. Now connecting the two pulleys is this steel belt, which has to be flexible enough to go around these pulleys, yet strong enough to transfer the torque. Now taking a look from the side, the way this continuously variable transmission is going to vary its input to output ratio is by changing the effective diameter of the pulleys from the input to the output. So for example, in this case, the pulley is adjusted so that the belt has the smallest diameter on its input over here and the largest diameter on the output. So this is going to give you a very low gear ratio, which is good when you want to start off from the stop. You can see as I turn this input shaft 2 full rotations, this output shaft here turns 1 rotation, so there's a ratio of 2 to 1 here. Now a low gear ratio like this is ideal when you want to start off from a stop, because your engine can spin faster than your wheels, and that's going to give you a torque multiplication. Now of course, in the opposite scenario, this diameter here would be the larger diameter and this one would be the smaller diameter, and that will give you an overdrive ratio. So let's say for example, if this was the driving gear and this was the driven gear, you can see that barely 1 rotation of this gear here is going to give me 2 rotations of this gear here for a 1 to 2 gear ratio. So that's going to work when you're on the highway and you want your RPMs to stay nice and low for good fuel economy. So now we need to take a look at how does this pulley actually vary the effective diameter of this belt. Now if you look at the cross section of the belt here, you can see that it's got a width, and that width is always fixed. However, the sheaves themselves here, where the belt actually rides up against, has a smooth conical shape to it, and this conical shape is the key to allowing this belt to adjust. When you squish this together, this belt is then going to be forced outward along this conical shape here and effectively change the diameter from inside of there to outside here, and that's because the width of this belt here has to remain the same. It can't squeeze the belt, so it's actually forcing the belt to come back out this way. Now of course, as this belt here rides up to the outside, its perimeter is going to increase, and that slack has to be taken up somewhere because the belt itself has a fixed length. There's no adjuster pulleys or anything, and that is going to be done by the secondary pulley over here. Now this driven pulley is responsible for doing the opposite of what the driving pulley does, and that is if the diameter increases on this side, it's going to decrease the diameter over on this side, and that allows you to maintain the same chain length across the two because the center to center distances are fixed. Therefore, any increase on this diameter must be mimicked by a decrease on this diameter in order for everything to work properly. Now, on some CVTs, these actuators are adjusted by hydraulics, and on some they're adjusted by an electric servo motor that actually moves it in and out. This one here is hydraulically driven. You can see these here are the ports where the oil is going to flow from the transmission casing into these hydraulic actuators to vary their widths accordingly. Alright, now I'm going to remove these pulleys from this casing here. And of course I got more oil dripping over here, so I'm just going to come in with my wife's something here and wipe this up. Hope this video doesn't get flagged for being too dirty. And here we've got the pulley system removed from the CVT housing. Now these brackets here are what was holding it to the housing, and on the end here we have this bearing and this bearing over here. Now there's 2 large nuts on this side here and then 1 large nut over on this side here that I need to remove, but I ain't got no socket that big, so I might have to improvise. Time for the angle grinder. There we go, busted the nut. And then just pop off that bearing there. Driven side has this little circlip here that I'm going to remove. Just made a little incision over here on the driven side. I'll pop off this cap here. This looks like a fluid chamber or something. Alright, so I was able to pry this belt off of the pulley here so I can separate these two. There we go. So here now we have the actual belt itself. Here we have the driven actuator, and this is what's going to change its width with that conical shape. And here we have the driving actuator, it comes from the input shaft. Now taking a look at the input and the output actuators, these are hydraulically actuated. You have the cone sheave part over here where the belt itself rides up against, and adjusting this width here using hydraulic pressure inside of this cylinder is what's going to either draw this back or push it forward in order to vary that belt diameter. Now the hydraulics on the input shaft come in through this part of the shaft over here where the planetary gear set actually butts up to. Oil pressure is then going to enter inside of here and fill up this chamber over here, which is going to slide this back over here, reducing the effective diameter over here. Now on the output side variator, hydraulic pressure is going to enter in through here, and it does that through the transmission casing where it has this port over here that feeds it directly. That actually leads up to this port over here, which goes back into the valve body of the transmission. Now the belt here is probably the star of the show. It's made up of these individual small little pieces of steel over here that form around this belt, and that overall makes this steel band very flexible and still strong and able to transfer torque. Now unlike a rubber belt where there's always tension on this belt because it's a pull style system, these belts are a push style system where the driven part actually pushes these little steel membranes together in order to transfer torque over to the driven side. I'm just going to pull out this little steel band here so we can have a better look. Now taking a look at these little elements here, you've got these two slots over here for the steel bands to hold the whole thing together. You've also got this little dot on the top here. Now this little detent is going to plug into this little imprint on this side, just like that, and that is what's going to give the belt some gap on the bottom there when it's in its straight section, yet allow it to compress when it needs to curve around the pulley. Now in addition, the angle of these elements here have to equal the angle of the cone over here so that it can freely move up and down. So now that we've taken apart this Nissan CVT, let's take a look at some of the failure modes, starting of course with this belt, which is probably the weakest link in this system here. Now this is just a steel band, it's no hard gears like in a manual transmission or even planetary gears like in an automatic transmission, and transferring too much torque to one of these could eventually cause it to fail itself. Now one of the worst things is that Nissan's chosen to attach this to higher powered vehicles. CVTs are mostly known for lightweight vehicles such as economy cars, but for some reason they chose to pair the VQ35 engines to this, which is a pretty powerful engine, and that's what's going to cause these things to fail. People are going to load those vehicles up, and that's not going to do well for this transmission. Now another factor that can cause this belt to slip or shudder on these cones here is of course wear and tear. Now not only can wear and tear happen on these cone surfaces or the belt, but a slipping or a shuddering can actually happen if these variators aren't doing their job properly. For example, if this variator adjusts differently from this variator, all of a sudden the diameters are not the right ratio, and then this belt starts to slip and shudder. Now perhaps one of the biggest oversights by Nissan was the cooling system, and that's because it was inadequate for these CVTs. Now these CVTs do generate a lot of heat because you do have this belt system, and if the cooling system can't keep up and the transmission fluid can't absorb the heat, well then all of a sudden you have parts that start to disintegrate and wear out much faster because they're at much higher temperatures and they just self-disintegrate. Now one of the telltale signs of CVT failures is a whining sound. They definitely do make a lot more noise than a conventional automatic transmission, and that's because you've got a steel on steel contact over here with a rotating assembly. Now although as things do start to wear out pretty fast, these are known to keep a lot more noise. Now because you've got a planetary gear set with this style of clutch, just like an automatic transmission, this can also be a failure point as well. If this does fail, then your CVT is going to fail to go into drive or fail to go into reverse, or get stuck in reverse, and then you're literally going to be driving back to the dealership. Now of course CVTs do have their advantages and disadvantages. With a belt system you don't have any gears to worry about, which means that you got really smooth power delivery, unlike in an automatic transmission where you got these clutches that keep locking and unlocking up, giving you brakes on the power band when you're accelerating. Also because you got less clutch packs, there's less friction, and therefore CVTs do give you better fuel economy. And that's the number one reason why a lot of makers of economy cars are switching towards CVT transmissions, because the drivers of these economy vehicles typically don't care about the driving experience that you lose with the CVT, but they care more about the gasoline that they're going to save. Now of course that fuel economy does come at an expense, and that's because this belt does make a lot of noise, but not only does it make a lot of noise, it also kind of gives you a rubber bandy effect. You see, the thing is, with a clutch pack you can instantly lock and unlock this with just a change in pressure on your valve body, whereas this big drum over here, you got to fill this drum up, and thus when you floor the gas pedal, it's going to take a while for this variator to change its ratio for you to accelerate fast. Now Nissan does market their CVTs as more reliable than conventional automatics because they've got fewer moving parts. Now while that's true, they definitely aren't more reliable. There's been tons of these failing out there, so much so that Nissan's been involved in a lot of lawsuits and settlements over owners with CVT transmissions that don't even last the warranty. Also, unlike an automatic, you see everything I've done here has been done on my own part. There's actually no manual on how to take apart a CVT and properly diagnose it, or any parts available, or any diagrams other than this one little cross section they give you in the owner's manual on how this thing works or how to repair it. When your CVT fails, you're out $3,000 or $4,000 to completely replace the entire thing. There's no rebuilding of a CVT transmission the way you would with an automatic. Now all in all, if you do happen to own a CVT vehicle, the only thing you can really do to prolong its already shortened life is to keep up on your transmission fluid changes, your coolant services, and to drive the car pretty easy. Don't do any towing, even though you've got a Pathfinder or a Murano that's supposedly rated for it, because you could easily damage these expensive components in your vehicle. So the next time you use your paddle shifters to shift your CVT transmission, think of all these components that have to go inside to make it work. Now make sure you follow me on Instagram for more behind the scenes footage, and subscribe for more videos just like this one.